about the three-phase induction motor and its basic principle of working. And in my last class, I just started about the equivalent circuit, how to find out the equivalent circuit of the induction motor. That I just started. And I told you just to listen what I am telling first before writing anything else. See, the idea is that a three-phase induction motor has got a balanced three-phase stator winding and a rotor winding and rotor winding will be kept usually shorted so that it can produce torque, rotor can carry current, etc. Now, what I am trying to tell, you imagine first that these are open, rotor terminals are open. Now, if you apply three-phase supply, a rotating field will result, Fs, stator field, and it will start rotating with ns speed. And there will be induced voltage in the rotor. However, there will be no current in the rotor. So, total MMF acting in the machine is decided by the magnetizing current, whatever is drawn, balanced three-phase magnetizing current by the stator, and the flux, as we know, will induce voltage in each of the phase, and this voltage will be balanced by the supply voltage per phase to satisfy the KVL equation. Is not? If I neglect the stator winding resistance, leakage reactance drop, then this applied voltage should be equal to the induced voltage on the stator. However, the moment you close the rotor, there will be also balanced three-phase current flowing in the rotor circuit. And this current will also produce a rotating magnetic field. And I showed last time that with respect to a stationary observer, the speed of this rotating field produced by the rotor is how much? With respect to a stationary observer? Ns. At least let us consider at nr equal to 0, suppose. Speed is 0. Rotor speed is 0. I have just switched on the supply. Then the rotor field too will rotate with a speed ns, because at that time the frequency of the current is f. But so there will be additional MMF coming in the machine. But the flux per pole cannot change because it has to satisfy KVL in the primary side. Therefore, stator now will draw additional current, additional balanced three-phase current from the source, such that the additional current, if it draws, it will produce another rotating MMF, and it will draw that current in such a way that it will counter this rotor MMF, such that once again the flux per pole will remain same in the machine as decided by the no-load magnetizing current. Just like transformer, it will happen. But the point I want to tell, whether the machine is at stationary condition, suppose nr equal to 0, then what is the frequency of the rotor current? Rotor current frequency is F, supply frequency. And what will be the field of the rotor? Rotor field, if I call Fr, it will be also moving, mechanical speed will be ns, because number of poles be like that, ns same speed, in the same direction it will rotate. Therefore, stator, by drawing extra current, stator can draw only 50 Hz current, and that it will draw. And I know by drawing 50 Hz current from the supply, stator will produce a rotating field of frequency of speed ns. Therefore, stator can counterbalance such a field if required by drawing extra current from the supply. Now, this is also true when the rotor is running. What I am trying to tell. Suppose rotor runs with some slip, that is, it is closed, and rotor speed is suppose nr, mechanical speed, and suppose the stator is supplied from balanced three-phase supply. In this case, rotor frequency is how much? Fr is Sf. What is the speed? So the frequency of rotor current will be of this frequency Fr. What will be the speed of the rotor field? Speed of, in this case, where nr is finite, nr is having, not 0. when NR not equal to 0. At that case, rotor will have currents of frequency Fr and balanced three-phase current it will be, and its speed will be speed of rotor field, speed of rotor field will be how much? N equal to 2F by P. So 2Fr by P, the mechanical speed I am calculating, 2Fr by P. This will be the speed of the rotor field. But what else should I write with this speed? Only speed with respect to what? Not stationary, with respect to rotor itself, because rotor now houses the winding. This must be understood. Rotor current frequency is Fr, balanced three-phase current, and rotor winding is housed in the rotor. But rotor is, so with respect to that winding, with respect to the structure which houses the winding, this is the speed. So this is with respect to rotor, this speed is. Therefore, with respect to stationary observer, what will be the speed? With respect to stationary observer, I will write it in a bigger way. So, when NR equal to not equal to 0, rotor field speed is equal to 2Fr by P, so much of RPS, mechanical thing, mechanical. And this is with respect to rotor, because rotor houses the winding now. Therefore, with respect to a stationary observer or stator structure, with respect to a stationary observer, the rotor field speed will be equal to 2Fr by P plus NR. This will be the speed. This, if you calculate, how much it will become? You put for Fr 2SF by P like this, plus NR you put. 2F by P is NS. And what is NR? NR is 1 minus S into NS. And this, if you calculate, this will become NS. Therefore, a stationary observer will see the rotor field rotating always at NS, no matter whether the rotor is stationary or rotor is rotating with any arbitrary speed. This is very important thing one should note. That is, in an induction motor, rotor speed may vary, NR may vary, as I told you earlier, because of change of load, etc. If you could see really the field lines, etc., suppose let us imagine we can see the rotor field will be moving field, but with respect to a stationary observer, as load changes, rotor speed changes, but he will always see it is moving with NS. Therefore, stator winding, what I am trying to tell, that stator winding of the machine has to react whenever there will be a rotor current, because it has to keep the flux, it has something to fulfill, because voltage balance, etc., in the primary circuit is to be maintained by KVL law. So the moment whether rotor is running or not, when the rotor circuit are closed, stator really cannot distinguish it. Stator always will react to what? As if somebody has produced a rotating field which is rotating at a speed ns with respect to the stator winding. Therefore, stator has to always counterbalance a field which is moving with ns produced by rotor, no matter what is the speed of the rotor. That is very important. And that it can nicely do, because stator can only draw 50 Hertz power. So by drawing 50 Hertz current in its circuit from the supply, it too can also produce a rotating field moving with ns, and therefore it is always eligible to cancel that out, no matter what is the speed of the rotor. This must be borne in mind. You should understand this point. That is, no matter what is the rotor speed, stator winding will always see rotor field is moving. Suppose a stator winding is asked to counterbalance a field, and it knows that that field, what it has to counteract, moves always with a speed ns. And stator is quite eligible to produce another field which will rotate always at ns speed, because 50 hertz supply. So it will, by drawing extra current, it can counterbalance that one. Therefore, this point is important. No matter what is the value of rotor speed, so you can write this in language, that no matter what is the value of nr, the field, the speed of the rotor field, appears to be always ns, the synchronous speed, with respect to stator winding, or for that matter with respect to or any stationary observer. This is a fact. Okay, now we were discussing about the equivalent circuit, how to draw it. Now, equivalent circuit that we discussed, started earlier. Equivalent circuit. It appears that equivalent circuit of an induction motor can be developed in the same line as that of a transformer, because there is a primary winding, secondary winding is loaded. Loaded means here it is shorted. So extreme kind of loading you can think of. So what we will do is this. So suppose per phase equivalent circuit I am drawing. It is very easy, and I can start drawing with this one, say approximate equivalent circuit, like this, or exact equivalent circuit. It will be something like this. And this is your, suppose, ideal stator winding per phase. I will explain each one of them, but let me first try to correlate this one. With respect to the stator, there will be, say, stator resistance per phase, there will be stator leakage reactance per phase, XL1, and there will be a resistance representing the core loss and the magnetizing current. And this is the ideal stator winding. And this fellow carries current whenever there is a current on the secondary side. So this voltage is your E1 voltage, induced voltage. And this is your applied voltage per phase on the stator. And let us also assume the machine is running at some RPM, NR, as a general case. Or say at NR equal to 0 first, standstill condition. See, standstill condition thing is pretty easy, because of the fact, if rotor is not allowed to move or it is not moving, rotor is shorted, you have energized the stator. In that case, there will be stator induced voltage also per phase. Rotor. This is the rotor per phase. What is the magnitude of the induced voltage? E2, where we know the magnitude of E2 by E1 is N2 kW2 by N1 kW1. This we have seen. So this is the rotor induced voltage per phase, and these rotor terminals are shorted. So per phase shorting will also appear. But the current in the rotor circuit will be limited by what? by the rotor per phase impedance. Induced voltage and you have shorted external no impedance is there. So here what will come? Some R2 will come and a rotor leakage reactance will come. This instead of L I will write simply X1. X1 is the leakage reactance. Leakage reactance per phase of stator. And X2 is the leakage reactance per phase of rotor, and something else also I have to write, that I will tell. Now suppose this is the leakage reactance of, because you know reactance is 2 pi f into inductance, is not reactance value. And in case of induction motor, peculiar thing happens. The frequency in the rotor current changes, unlike a transformer. Therefore, while defining this X2, I must specify at what frequency I am defining that. So what is done? X2 is called leakage reactance per phase of rotor at standstill condition. This one should remember. At standstill condition. This is important. So at standstill condition, the equivalent circuit is just like this. At standstill. NR equal to 0. This will be the equivalent circuit. And what is the frequency of stator current? It is always F. What is the frequency of rotor current? I will write E2 and F here during standstill condition. So during standstill condition, the equivalent circuit referred to primary side, say, is just like a transformer, no problem at all. This voltage frequency, this voltage frequency, frequencies are same. Therefore, equivalent circuit referred to referred to primary, and of course per phase, can be just done like the transformer. This is exact equivalent circuit, something like that. R1, X1, there will be the parallel branches here. And here it will be something R2 dash I will write, where R2 dash equal to S square into R2 I will write. And here I will write the S square into X2, that is X2 dashed. And I can do, because it is just like a transformer. Frequency are same, both in rotor and stator, like that. Okay, while this is true at standstill condition, whether this will be true also at some speed when the machine is running with some slip or with some finite NR. That is what we will examine now. Now what happens? What happens when motor runs with a slip other than 1? S equal to 1 is your standstill condition. That is, there is some NR, that is NR not equal to 0. What I mean by this statement is simply this: there is some NR not equal to 0. Now let us see. Then this primary thing remains same. This is R1, this is X1, and this is your parallel branch. It is like this, and this is your this ideal thing here, E1 voltage, and here is ideal thing here. Then this is the exact rotor thing. What should I write here? You tell. What is the voltage here? If this is E1, what? S into E2. Because E2 is the voltage during standstill condition. E2 is the voltage during standstill condition. Therefore, when the machine runs with a slip, we have seen the induced voltage per phase in the rotor, magnitude of that voltage will be SE2. and then here. And as I told you, you should also write what is the frequency of this voltage. What is the frequency of this voltage? SF. It is not F now. S into F, other than your supply frequency. Then what you have? Here you have actual rotor resistance per phase R2 and the leakage reactance, the winding resistance and leakage reactance. What should I write here? AS into X2, because this also will reduce by the same factor, because twice phi FL, whatever is the leakage inductance, that is X2. So another S comes. Where, so X2, remember, it is the standstill reactance, and S is the slip at which the machine is operating. Now the question comes, here of course some current will flow in the rotor circuit if I look at, but the frequency of this current is SF, and frequency of the stator current is, that will always remain F, because as I told you, stator will react when there will be a rotor current. And because of that interesting fact that no matter what is the rotor speed, stator really does not know. Machine is running stop or it is running with some speed. It always will see the secondary winding has produced a rotating magnetic field which is rotating with ns speed. And it will say that I can always counter this fellow by drawing 50 Hertz current, because it can produce ns speed rotating magnetic field. That is the idea. So that is there. But now joining these 2 points is not permissible, because it is supply frequency F and SF. Coming to the equivalent circuit, suppose I want to draw the equivalent circuit of the induction motor when the speed is not equal to 0. Then what should I do? That is what I am now going to tell. You get it? Now let us assume the magnitude of the rotor current. This is the exact rotor thing, what is happening. This is the induced voltage magnitude. Suppose I2 is the magnitude of the rotor current, R2, SX2 at the impedance. So in the rotor circuit, magnitude of rotor current is obviously AC2, magnitude of the voltage, under root R2 square plus S squared X2 squared, straight. This is the magnitude of the rotor current. And also, what is the frequency of this current? SF. Frequency. This is frequency of this current. This we should remember. This is the frequency of the current. This is the magnitude of the current. Now let us see, this current flows, and the MMF produced by the rotor, that amplitude of that MMF or field will be proportional to what? I mean, I don't want to put that rotor term. What I am telling is, in a 3-phase winding, balanced 3-phase winding, suppose the magnitude of the current is known, RMS value of the magnitude of the current is known, and the winding is known to be a balanced 3-phase distributed winding. What is the strength of the resultant field? We have calculated. It is some 3 by 2. It is proportional to 3 by 2 into number of turns per phase into the magnitude of the current. And there that frequency does not come. What I am trying to tell, the amplitude of that field, resultant field, what is the strength of that field, is 3 by 2 into n into RMS value of the current. Or are you getting 3 by 2? That magnitude of the current comes, Imax or something. In fact, Imax, it is Imax. You remember this figure, K, you can just go through. Where Imax is the maximum value of the current decided by the, here no frequency comes. The amplitude of the MMF is decided by this. You pass 50 Hertz current, suppose current is drawn 5 ampere, whatever will be the amplitude of MMF, if you pass same amount of current at 25 Hertz, the strength of the field will remain same. Now, with this one, this I2 current will then decide what will be the field strength of the rotor. That is some K into rotor turns per phase into the I2 max, etc. It will be there. And this one, it will be balanced by the stator, this K1, N1 into I1 max. That way the rotor stator current gets fixed like transformer. MMF is to be balanced. Now, the point I want to make, this is okay. So, it will draw this one. Have you understood this point? I mean, I have not told many important things here, but the message is clear what I want to say. So, this is the exact rotor current whose frequency is SF, and it produces a rotating magnetic field which will move with a electrical speed of SF, and the strength of this one depends upon the magnitude of the current like that. Now, what I will do a trick here. See, now this current I2, this expression of the current, I will divide both sides by numerator and denominator by S, term S. So, this is E2. And this one will then become R2 by S whole square. This one will become X2 square. You simply divide by S. Okay. Now, what I want to tell, this you listen carefully. This is important. This is something conceptual. Your actual machine, this machine has got a per phase rotor resistance R2 and per phase standstill reactance of X2, and the machine is running at some speed other than 0. I am examining what is happening. That is what I am doing, how stator will react like this. Now, I will ask you, you imagine a conceptual machine, which is not this machine, whose rotor impedance is standstill rotor impedance is R2 by S and X2. I will explain it once again, but let me first tell what I am trying to tell. Suppose you imagine there is another induction motor whose rotor resistance is R2 by S at standstill, and its leakage reactance is X2. Not this machine, another conceptual machine I am imagining, whose rotor impedance at standstill is having R2 by S at whatever slip this present machine is running. Suppose I imagine there is an induction motor whose resistance per phase is R2 by S and whose standstill leakage impedance is X2, and that machine is under standstill condition. Okay, just rotor is replaced by this one. Now, suppose for this machine, same stator winding is there like the previous machine, the supply is given on. At that time, the induced voltage here will be E2 and frequency of this current will be F. And in this conceptual machine, imagined machine, imagine a rotor whose standstill impedance is like this, and stator is energized with usual voltage. And at that time, what will be the magnitude of this current in this imagined machine rotor? Same I2, because it is E2 by R2 by S whole square plus X2 square. Okay. What will be the frequency of that current? F. Now the question is, stator will react to that and it will draw extra current. Okay. Now, my question to you is this. In these two cases, when this machine is running with some speed, NR, with a slip S, can the stator distinguish between these two cases while reacting to it? It cannot, because of the fact that in the magnitude of the current is I2, although frequency is F. But stator always will be just seeing somebody has produced on the secondary side a rotating field which is moving with NS RPS. The magnitude of that current, that field strength, and the speed that it will only check while drawing extra current to counter that MMF. Therefore, what I am trying to tell, the rotor cannot distinguish between these two rotors. Suppose you have machine is running, this is the actual condition of the machine, and you now take out that rotor, replace it by another rotor with this resistance. Of course, this S value, whatever S it was running, that S as if you have put, and X2 is the same leakage reactance of this machine. Then the secondary current magnitude is same as this one, frequency is F, and a rotor will draw the same amount of current and that same power factor, just like the previous one. Now, if this we can do, then there is no problem. Are you getting? But there is only one word of caution here. Tell me, what I am not doing is this one. I am not telling that these two circuits are equivalent. What I want to mean to say is this. Suppose actual rotor circuit. This is the EMF, actual rotor circuit. There is a source of EMF here. And this is the rotor resistance R2. And this is the actual thing in the rotor, R2 SX2. And now what, and the frequency of this one is SF. Now, in this circuit, that is E2 standstill induced voltage, and as if this one is this, R2 by S, and this one is this. This frequency is F, you should remember. What I am trying to tell, these two circuits are not equivalent in the normal sense. What is the objection? The magnitude of the currents are same. I cannot say these two circuits are equivalent. Two static circuits are there as if I am drawing this is one-to-one correspondence, not like that. What is the problem? Frequency is one problem, and another problem? Magnitude of the current is same, but power is not same. See, what is the power, real power involved here? I2 square R2. See, wattage involved here. What is the wattage involved here? I2 square, same current magnitude. I2 square into R2 by S. Power is not same in both the circuits. In which case power will be more? This circuit or that circuit? Second circuit, because slip will be always less than 1 when the machine will be running. Then where is the, how to take this power change in these two circuits? See, in the first case, it is not very difficult. In the first case, you are sitting on the rotor, and I2 is the current. What is the power loss in the rotor resistance? Rotor resistance power loss is I2 square R2, actual rotor resistance power loss. See, that is the original machine, you just think, forget about this part. In this machine, when the machine is running with a slip S, actual rotor current is I2. Power loss in the rotor winding resistance is I2 square R2. And power drawn from the supply will be this reflected current with some power factor will come. Where that remaining power is going? The balance of the power, that mechanical power, it will be going. Now, once I have gone to this imagined conceptual machine where I am thinking the rotor is stationary, this I2 square into R2 by S will give you what? The total power, including the rotor resistance loss per phase and the mechanical power. Because rotor I have brought it to 0, so the resistance value is increased in order to take care of that mechanical power. Are you getting? In fact, this circuit, this is, I have considered it to be stationary. No, this circuit, if you do it like this, E2 is the voltage, and this is the actual rotor resistance is R2, and this resistance will then be 1 minus S by S into R2. This resistance I can see in two parts. So what I am trying to tell, Here I2 square R2, here I2 square R2 will be same. But another thing comes to take into account this mechanical power developed by the machine. Anyway, this I will once again take up at appropriate time and try to highlight. But what I am trying to tell, that our initial problem of connecting these two circuits can be removed if you imagine that this will be I2, but this you replace by E2 and this by R2 by S. That is as if you have divided by S all the sides. Therefore, equivalent circuit, I mean the stator at any speed S can be drawn like this: R1, X1, and this is the leakage reactance per phase, and this is the this ideal winding. And on the rotor side, what you do, you write it here E2, write it here E1, and here you write R2 by S, and here you write X2, and as if this frequency is F, this is this I2 will be there. Here will be some reflected current I2 dashed like that, following the same rule because MMF is to be balanced. And then I can join these two, what I mean to say, without any problem. That is, after this, what I will do is this. R1, I mean, I will draw in the next page. So these two sides can be joined with confidence. That is, this is the stator impedance, R1 X1. This is the equivalent the core loss component of current, etc. And this one, what should I write? R2 dashed by S, which is equal to S square into R2 by S, where R2 is the actual rotor resistance. And this will be X2 dashed, which is equal to S square into X2. Remember, X2 is the standstill leakage reactance of the machine, rotor, and R2 is the rotor resistance per phase, and so on. Then by doing this, if you analyze this circuit, I am trying to tell, if you calculate this current here by analyzing this circuit, this current square into R2 dashed by S will give you what? It will give you the rotor copper loss plus the mechanical power developed in the machine. Okay, see this current square, this is suppose I2 dashed. So I2 dash squared into R2 dashed by S into, of course, 3. There are 3 phases per phase. This will be equal to rotor copper loss, total rotor copper loss, plus mechanical power developed. And that is, this one will be equal to, rotor copper loss is how much? This is I2 dash square R2 dashed, straight. Actual rotor resistance is R2 dashed with referred to stator, and actual, I mean deferred current is I2 dashed. So actual, this is 3 times I2 dash square R2 dashed. And then the mechanical power is mechanical power. So you can see mechanical power, P mechanical, will be this 3 is there, I2 dash squared R2 dashed by S, minus 3 I2 dash squared R2 dashed, and which will be equal to 3 into 1 minus S by S into I2 dash squared R2 dashed. It is precisely for this reason this resistance is often shown divided into 2 parts in the rotor circuit. That is, you draw this one, primary, this thing, and this one is there. And here you can show it like this. This is the rotor actual resistance R2 dashed. Then your leakage reactance X2 dashed. Then you show, because these are all series, you show it like this, that is 1 minus S by S into R2 dashed, which will represent this power in this resistance will give you the mechanical power developed in the machine. And also in the equivalent circuit, it is this resistance is shown variable instead of fixed value. Also here, that R2 dashed by S, it is shown variable. Tell me why? Because the S will be changing depending upon the load torque present on the shaft of the machine. So at a, of course, particular value of slip, this is constant. Okay. Now, I will tell you about one thing before I calculate and go on further with this one. That you imagine it like this, that on the stator you have given some power. Input power is given to the stator. Let us see, from that if I go on subtracting the various losses, I should reach this mechanical power output on the shaft of the machine. Now you give input power. So from that input power, if you subtract this stator copper loss, you subtract, is not? Then you subtract the core loss power. Is it? These two loss you subtract. That remaining power, as if it crosses the air gap, now enters the rotor. Like that you just conceptualize. That is, I have given some input power. That is, if I draw like this, there is some input power given. This is some P input I have given. Then from this, a portion will be lost as some stator copper loss. P copper loss, stator. Then there is some loss is subtracted from this, that is the core loss. That is the power flow diagram I am trying to visualize. Then this power now is called, now from this what else we have to subtract? The rotor copper loss. Now at this level, this power is given a name. This power. That is, after subtracting the stator losses, this power is called air gap power. As if this power is crossing the gap and entering, like that you think. That is, this power enters the rotor. From this you subtract what? Rotor copper loss, P copper loss, rotor. And then you get here, this power should be called gross mechanical power. P mechanical gross. Total mechanical power developed. And net mechanical power, how will you get? From this, you subtract the mechanical losses, frictional losses. That is also mechanical power machine has to develop, but it will not do any useful work for you. So you subtract the P mechanical loss. P mechanical loss. And here, this one will be your P net mechanical. P mechanical net. This diagram you should keep in your mind. Okay. Now, in terms of equivalent circuit, what is this P air gap? I will write PAG. This is what? P air gap. It is 3 I2 dash squared R2 dashed by S. P rotor copper loss. P rotor copper loss is how much? Tell 3 I2 dash squared R2 dashed. So you see this happens to be equal to S into PAG. These are very useful relationship while solving problems. See, air gap power multiplied by slip at which machine is operating gives you the total copper loss. And P gross mechanical will be PAG air gap power minus S into rotor copper loss. And this will be equal to 1 minus S into PAG. That is, this of course you should not have this idea, but what I want to tell, that is air gap power is to the rotor copper loss is to gross mechanical power will be in the ratio of, if this is 1, this will be S times of this one, and this will be obviously 1 minus S. This you should remember. In that ratio it comes. Suppose you want to find out what is the torque developed by the machine. How do you find out? T gross mechanical developed by the machine will be how much? Power, gross mechanical power divided by its mechanical angular speed. That is P gross mechanical divided by 2 pi what? NS or NR? NR we have to write. Actual rotor speed, mechanical speed. And P gross mechanical, as we have seen, this is nothing but 1 minus S PAG. And also we have seen that for NR I can write 1 minus S into NS. And this becomes equal to P air gap power by 2 pi NS. So you remember that to calculate the gross mechanical power developed by the machine, either you calculate actual mechanical power developed by the machine divided by 2 pi NR, or simply you calculate air gap power. Don't go up to that extent. Simply divide it by synchronous speed, which is constant. This thing is constant of the machine. It does not change with loading. Therefore, in other words, we can say air gap power is a measure of torque developed by the machine. Gross mechanical torque developed by the machine is same as the air gap power. Sometimes, so the unit of this one will be what? Torque unit will be Newton meter. It will be. So sometimes it is torque is also expressed in synchronous watt. That means if air gap power is, suppose in a particular machine you calculate air gap power is say 1000 watt, you tell also torque developed is 1000 watt. Sometimes with this in mind, that actual torque in Newton meter will be this 1000 divided by 2 pi ns. So sometimes torque is also used in watt, and that is called synchronous watt. So these are very useful formula, you should remember. Okay, this power flow diagram, of course, in later stage will slightly approximate whenever it is needed. Because see, I will tell you the problem only today. What is the problem in this power flow diagram? See, unlike transformer, see, in a transformer, when you do open circuit test, secondary is open, no current is flowing in the secondary side, and current drawn, power drawn, etc. you measure and get the value of RCL, XM, etc. this parallel branch impedance. Now in induction motor there is a problem. Suppose I want to do no load test. Okay, that means the machine is to be run, no load means what? No load torque is connected on the shaft. It is not running a pump or doing some mechanical work, cutting a tool like that. On the shaft there is no load. Therefore, at that time, if you energize this one, at what speed machine is expected to run? Very close to synchronous speed, but not synchronous speed, running below. See, ideally, if it could run right at synchronous speed, what would have been the value of S? 0. And if S is 0, then this branch would have been an open circuit. And you could perhaps measure RCL extent. Anyway, today I stop here, and next time I